So thank you very much for presenting plandres to us today. And no, you can speak.
Okay, well, thank you very much for inviting me to this nice symposium. I think it's the very first public presentation of the plandres project that has just begun. So please excuse me if it's not that clear. So I'm Sandrine CHAROUSSET, I'm from EDF, and I have the great pleasure of being the coordinator of that nice new project, which has a name that's a bit complicated. I won't read it. This project will be very closely related to what we have seen yesterday and today, because well, energy and climate is very much linked. And so first, this project began the 1st of November, through 4 months ago, for 3 years, and there are, well, the consortium is described here. We have, well, it's coordinated by EDF, and then we have another industrial, which is Siemens, which is another end user for the tool that we are going to develop. And we also have academic people, which are specialists of power system and of optimization methods. And then we have the third industrial, which is a Cray Computer, which is specialist of IT and parallelization, because we are going to develop tools that need very efficient high-performance computing. What are we talking about here? It's well, not forecasting. We want to develop, well, the question asked by the Commission was the need for some new end-to-end planning and operation tools for the pan-European energy system. So this is the topic of the project. It will be focused mostly on the electricity system, but we will also look at the interactions with other energy vectors, like gas, heat, cold mobility, because when you are looking at emission targets, it's just impossible to separate between electricity and the rest of the industries that emit CO2 or other things. What we want to have is the most realistic possible representation of the system operation that's take into account all dynamics of the system, all operational constraints of all the power plants and interconnections. The objective, of course, is to look at the variable renewable integration with all the increasement of renewable generation. We have a special focus on how to model and take care of uncertainties, because, well, variable renewable is variable, it's not very much predictable, so we really need to deal with that, and especially with the link to climate. And what does end-to-end mean? It's that we need tools that represent the system from well, end-to-end, from generation to consumption, from the high European level to the very small scale level. We are not going up to the house level, but that will be in the future in another project, hopefully. So just an introduction about what do we mean by energy management tool. So there are two different scales. We need some tools for managing the operation of the system. So operation of the system is mainly calculate the best schedules for all the generating plants, and of course the best strategy for the reservoirs management. And best strategy for reservoir management, it's the fact that it has to be coordinated between, well, it's better to coordinate reservoir management between different countries in Europe than to handle it separately. And this is a very difficult problem because well, we have to satisfy the equilibrium between generation and demand, because we can store electricity, but not that much. We have to take care of all interconnection constraints. The objective, of course, is to minimize the cost, to respect all the technical constraints, take care of uncertainties, and as the generation uncertainty from renewable is getting higher and higher, the reserve provision dispatch is more and more important. So we also have to define schedules that are that can take care of very short-term uncertainty, like outages, or just tomorrow there is no wind, so we have to use other generating means. So this graphic here, it's just something that's quite old. In the old days, when we only had a few, what we called that not controllable generation, that was the renewable run-of-river, things like that, and a lot of base load energy, that was the thermal, and we could follow the load curve with mainly the hydro and gas turbines, and that was done at the scale of each country. And today it's getting a bit more difficult. And then the second aspect is what we call planning. It's what is the optimal energy mix. So that there are energy mix already in Europe, power plants and a grid. But then we want to use those tools to make projections at the horizon of 2030, 40, 50. So the mix will be very much different. And we try to develop models to optimize it in terms of which generation asset, which technology, and where to build them. Storage, where is it interesting to build a new storage capacity, and which level of storage. Demand response, also demand response, it's when you ask, for instance, in big industries to lower their demand and they get paid instead of that. So that's centralized demand response, and you can also use as things in the houses of the people with the new metering systems, controlling their loads. And so this is also part of the energy mix. Then transmission grid expansion also. It can be more optimal to add, have a bigger line between two different areas than to build the power plant in one of the areas. And also distribution network reinforcement, because there will be more and more local system, and renewable generation is mostly connected to the distribution network, for instance, PV. And what is very important that in the location of all those assets. And so this is a map of Europe. So we won't work on this very detailed description with all the network, but more on sort of clusters models. And that's a good news because it's consistent with the data that are in ECEM. So what is changing mainly in Europe? It's the COP21 and the carbon reduction targets. We need to have an energy system that is sustainable, so with mostly green energy. We need to ensure security of supply, and we need it to be competitive. And this is just examples of that is the targets in 2020 in Europe, and evolution of RES integration from 2000 to 2015. So it's growing, and that is the projection 2020, and then we have other ones, but they're not in the graphic. That should be, the objective for 2020 were 27% renewable. So, and we hope to have a 60% renewable one day. So this is there are big changes because of that. So our planning and operational models were designed at the beginning 20, 30 years ago with big power plants and centralized dispatch. And now what is coming is well, a high share of renewable. 30% is already a high share, but 60% is big more. So it's unpredictable or less predictable, and well, it's getting more and more predictable with all the work that's going on. But it's intermittent, so it's not stable. This is very difficult for the electricity system. And so this means that we have an increased need for flexibility. Flexibility is all the other generation means that can run when there is no wind. For instance, there is no wind, you use a hydro plant or something else. And we will need more flexibility sharing in Europe, because the flexibilities are located mostly all in the same country. Some countries have less flexibilities than other ones. And since now flexibilities are not very much shared between countries, and this flexibility sharing will have a very high value for the energy system. Then we need to have the grid and the generation storage mix to evolve toward a system that can host those amount of res. So that's the first big change. The second one is, as I have already told, flexibility resources are mostly connected to the distribution network, which is also a big change. And so, and the planning tools that are used now have not been designed to coordinate centralized and distributed flexibility resources. So that's another change. We have to go from a country level, which is a traditional way of working, to a regional level or even less in the planning tools. And we built our project on this assumption that we need an integrated representation of all this for being able to capture the value of the flexibilities and to being able to design the best possible energy system. Because if you only model bits of it or parts of it, or only the country level, only European level, or only local levels not coordinated, you will miss things. You will miss costs, or you will miss value. And that's what our project will do. So we will, I say we will because it's just begun, but we only 3 months ago, we will develop an end-to-end planning and operational tool. So not just a big tool, but it will be composed of a set of optimization models with an integrated modeling. And this will be quite big, so we need an efficient IT platform for providing access to data and IT resources and high computing, high performance computing, and we need efficient solution algorithms. So that's why we have in the consortium mathematical optimization specialists. We will also provide a database of public data for feeding this kind of model. So maybe it won't be exactly completely complete, but this is a proof of concept, so it has to be usable. And we will also develop 3 case studies for showing that this tool is working. And this is where ECEM is saving the project, because we will absorb nearly all the data that are in ECEM for building our database. And then one of our case studies will be focused on climatic change. So just a small graphic to show you that all the set of models, but I won't discuss that very much. So we will be working. There is a model for multi-energy design of the optimal mix. One model will be focused on generation investment and one on transmission, and then we have all the operation simulation models, and everything is interconnected. So what is interesting and quite new is that this is the traditional models only focus on electricity, but then we will have the link with multi-energy local models that will be connected there. And those models, they are working at a very short scale, that is not 3 probably, you know that here. And we will need data at that very short scale, cells by something like 10 kilometers by 10 kilometers to design those things, especially for heat networks. So just well, graphic that you have seen many. We have to take into account all those uncertainties, mainly on climate or temperature. You all know that it has an impact on demand and also on generation capacity, not only wind power and PV, but also generation capacity for thermal plants when it's very, very hot. We have to stop the nuclear power plants because they cannot be cooled down, things like that. So we need many scenarios of all the possible futures. So we need the trends in the coming years, but we need also hourly scenarios, for forecastings. This for temperature, for wind, for sun, and for inflows to reservoirs. And all this correlated. And so this was nearly my last slide to show where we will use all those data from ECEM. So we will need all the profiles for electricity, renewable generation, and run of river and inflows. Oh, sorry. So this we will need all those data for the years what we are working on with an hourly scale, and for this we need, as we are doing making stochastic optimization to take into account uncertainties, we need to use 100 or 200 scenarios for all this, and we need to have those data at very low geographical scales, especially for distributed resources. And then what we are going to do with those models, some examples of case studies. We are going to make a specific focus on the electricity system, run all those models for the year 2050, taking into account all those uncertainty, and the objective is to evaluate the impact of the key factors on the cost of RES integration. For instance, we are going to make simulations with different levels of RES integration, 60%, 50%, 30%, sensitivity analysis on which flexibility potential can be used. So if we use flexibility potential from other energy vectors or not, sensitivity analysis with economical variables, and we will try to calculate the value of different kind of flexibilities. And then we will make also a specific focus on climate change, do that specific study with the ECEM projections without climate change and with the ECEM projections with climate change at the horizon of 2050. And the idea is to find out what are the impact on the optimal energy mix and on the operation of the system and on the costs. And this is my conclusion. So if you want to know more, we have a website, we have a link to Twitter, and there will be a workshop that will be held on April 11 at EDF Lab. If some of you want to know more about the project, you can contact me and come here and listen.
Excellent. Thank you very much. Thank you very much, Sandrine. I'm sure that there are a number of questions. We actually running out of time. I can take one quick question, and I'm sure there'll be a lot more interactions and discussions as we move on with the project. Rather than asking my own question, I ask. You asked too many questions. Sorry.
I just have the question. With this system, you can create like a perfect tool for using the right energy sources in Europe, but isn't it a difficult thing to make the commercial conditions to create that system with different countries involved? It's not enough just to say what is the optimal system. You have to create the commercial conditions to make the investments.
Well, yeah, but this is the idea of the project. It's what we call a fundamental analysis. It's not, we're not talking of prices and commercial conditions. We're only talking of costs and trying to make studies in order to know how the system will be, how can it work. It's a matter of operational, technical operation and only cost, but then this can be used by people to make studies to see if their investment can be profitable or commercial. But the first idea of the project is how can the electricity system in Europe in 2050 be sustainable, and how can it be reliable? Which kind of flexibility have to be added in order that the system doesn't go down? And then the question of if the investment are possible, if does the market pay well the investment, it's another question, and there are other projects about it, but it's not our topic.
Very good. Thank you for the clarification, Sandrine. And Sandrine probably staying for...
Yeah, I'm staying for lunch.
lunch. Yeah, so please come and see Sandrine, ask more questions. So